Hey everybody, welcome back to Computers and Computations. This week we'll be discussing the ethics of computation, and I'll talk a little bit about how ideas of the hardness of the computation can figure into ethical questions, perhaps. Okay, before we get going, I guess I should say that this week will have a slightly different flavor from other weeks. Previously, the focus was more on trying to explain the material. Since the whole idea of looking at ethical implications of computations is so broad, it's really not going to be possible to give any sort of meaningful overview of even the main debates in one seminar. So what I'll do here is I'll look at specific things we've had previously in the course, specific ideas there, and see if I can extract some ethical upshots. So this week has a bit more of the flavor of a research seminar as opposed to a talk course from previous weeks. Good. So the first part of the course, we looked at characterizations of computability, largely things like Turing computability, abacus computability. We saw they were equivalent and so forth. And then we looked at how these could be applied, right? This is when we discussed Lucas Penrose, functionalism, stuff like that. After that, we looked at computational difficulty. So we looked at P, NP and friends, and also quantum computation. And what I'm going to look at in this talk is how these ideas of computational difficulty, right, might figure into philosophical debates, and in particular might help us address ethical questions concerning responsibility. So with this in mind, there are two main arguments I want to try out. I'm not sure how good they are, but I'm interested to get people's feedback on them. I may turn these into papers if it does turn out that they have some legs on them. So the first thing we'll look at is possible ethical implications of Rice's theorem. I'll remind everyone of what that is in just a second. And then the second kind of argument we'll consider proceeds from moral realism. This is the idea that moral claims have objective truth values. When combined with mechanism, the view that the human mind can be simulated by a Turing machine, when we look at issues concerning the hardness of computations, we get some payoffs possibly for ethical claims we'd like to make. So these are the two directions we're going to examine in this talk. Right, so a substantial question about ethics and computations concerns who is responsible when computations go awry, and indeed what our responsibilities are as people who are involved in the designing and maintaining of computers. So failures of hardware and software can and have resulted in significant loss of resources, such as when a computer error results in a bank transaction going poorly, and have even been fatal in certain cases. So a recent example here is the software errors associated with the Boeing 737 MAX series that resulted in a huge loss of life. Now, in these cases, we want to ask, ethically speaking, who is responsible for computational failures? This is an important legal question, both for our current behavior. We want to know how we should behave now, what our responsibilities are, and also appropriating blame in contexts where things go wrong. Okay, for the purposes of this argument, let's put aside hardware issues and focus on problems with software. So here we have a situation where a program executes perfectly fine, but it fails to give the correct output or the output that we wanted. Now, there are two situations we might be in, ethically speaking. So one could be that the people involved in the design of the relevant software were aware of the particular problem, right? So they knew that there were issues with the software, but rolled it out anyway. Okay, now in this context, it's pretty clear that the people who are aware of the problem and did nothing about it are responsible for the failure. So I'll set this aside for now. I want to focus on two, and this is the case where nobody is aware of the problem. So people think that the problem is, or the software is running perfectly fine, but nonetheless it doesn't give the desired output, and we get some bad results as a result of the program running fine but not doing what we want it to do. Now, one might think in this second case that because people are not aware, they are not responsible for the software error. But this seems a bit too hastily. We do not, in general, immediately excuse people from blame or responsibility if they were unaware of a particular issue. So, for instance, I can be responsible if I miss obvious mistakes or I fail to follow known mitigating protocols. So I can be negligent, for instance, in securing your safety. You have an accident as a result of my negligence and I'm still responsible. But it might just be that I ignored a problem or didn't look for a problem that I knew that might be there. So it's not the case that I have to be aware that there's a problem in order to be at least partially responsible for the error. Okay, so we can think here, for instance, in the case of software, where I just don't test the software properly. Okay, it's really important software. It secures some very important safety feature, but I don't have it undergo appropriate testing. Okay, I might not be aware of the software issue, but that's because of an issue to do with negligence. Now, an issue here is that very few software issues are actually obvious, right? So I can do a lot of testing, for instance. That's an obvious thing to do, but even if I do a lot of testing, there can still be errors. And computer programs are sufficiently complicated that it's not always the case that the error is going to be obvious. In fact, in most cases, the error is going to be highly non-obvious, and that's why it makes it through to production, for instance. Okay, so first observation is that we have an obligation to run known debugging strategies up to a certain level. Okay. So I should at least, if I want to fulfill my obligations as a person designing software, minimally run known debugging strategies at least up to a certain point, right? There's a point at which we feel that we have done enough. I think this is a difficult question to say exactly where this should be, and this will depend somewhat on context. So again, I'm just going to put this issue aside for now. Okay, good. So with this in hand, let's ask the following question. Are we failing in our responsibility to develop debugging checking software or checking software? And this is aside from our usual debugging strategies discussed on the last slide, but we might ask, look, have we failed as a community, let's say, to develop the best possible debugging software? And what I want to do here is I want to argue that even if you think we can do better, there are limitations coming from the results about computability that we've been looking at that suggest that there are always going to be limits here. So first, let's look at Rice's theorem. Let's remember what this said. So This said, let C be any set of partial computable functions, and let A be some index set for these partial computable functions. If A is computable, right, so there is some Turing machine that just enumerates all these particular n, then C is trivial in the following sense. It's either empty or it's all the partial computable functions. So this tells you that for different kinds of program behavior, you can think of those as particular functions being in this particular C. There's no way of listing them in a computable manner. So we might already think, look, if this is really a theorem about, or can be construed as a theorem about program behavior, there are going to be significant limitations on what is computable in this context. Good. So Rice's theorem implies that there is no computable procedure for checking non-trivial program behavior, right? Now, checking that a program does what we want in general is generally, not computable, right? So, for instance, suppose I have some code, right? And suppose I try and make that code run faster. And I want to check whether or not the optimized code has changed the program behavior. By Rice's theorem, this is in general not going to be a computable problem. So we may have to live with this non-obviousness in code. There is a sense in which we just cannot develop perfect software that will allow us to check programs are doing what they want. And it might just be the case. Look, there's going to have to be a kind of human input at some point into these kinds of procedures. Humans generally cannot deal with thousands and thousands of lines of code. So in this respect, while we might say we haven't achieved exactly the debugging strategies we have, and we can improve debugging strategies all the time, it's not like we're failing through a lack of creativity to produce the kind of debugging software that will allow us to solve basically all the kinds of problems we might come up against when dealing with software errors. Now, there are two kinds of response we can consider to this upshot. So, number one is that we should look for approximate ways or probabilistic ways of determining behavior rather than fully computable ones. So an example here might be the use of neural nets, for instance, or kind of deep learning strategies to, rather than producing, yes, no computable answers, will give you some kind of idea of whether or not your code is running well, instead of just relying purely on human input. Good. So, my response to this is good. If that's an implication for the practice of software engineering that arises out of Rice's theorem, then I'm happy. This is a nice way that we should think about software, and this is an upshot of some results from computability. So I'm happy if we go route 1. In route 2, we're going to consider, look, Rice's theorem only applies in the infinitary case in the following sense. It's about computability in general. So as we've discussed before, these can be very, very, very large computations. For instance, it applies to exponential time algorithms as well, things like that. And perhaps mostly what we want to say is, look, mostly we're interested in debugging programs for feasible inputs, right? Even if I have some software controlling something very, very important, it doesn't really matter if it suddenly has failures after the number of atoms in the universe many steps. It matters more if there are failures relatively smaller computational length. So this is the second kind of response we might have, is just to say, look, maybe we are failing in not generating good debugging software, or closer to perfect debugging software, but for only feasible inputs. So one line of argument I'm considering here, and I should say that this is just an idea, the details, well, in progress is maybe a little too generous. They need to be really thoroughly checked out. So I'm not sure if this will work, but I think it's at least an interesting line of thought, is to say, look, a standard proof of Rice's theorem reduces it to the halting problem. So we say, look, if the index set is computable and non-trivial, then we could compute the halting function. We know we can't compute the halting function, so if the index set is computable, then it's the class of functions is trivial. Okay, so this suggests the following line of attack: come up with a bounded form of Rice's theorem. So come up with some kind of statement that involves a restriction to polynomial time or similar checkability, and then show that with polynomial overhead can be reduced to the bounded halting problem. So this is the halting problem, but only halting in under n many steps as the number n increases. Okay, so this is there's a substantial challenge here, is to figure out exactly what the formulation of Rice's theorem should be here. So exactly where we should figure out some analog of Rice's theorem using polynomial time somehow to formalize the notion of feasible input. So if we could carry this off, we could come up with a reasonable bounded version of Rice's theorem, and we could show it was reducible to the bounded halting problem. We'd have shown that the problem of analyzing program behavior for feasible inputs is an NP-complete problem, right? Why is that? Well, the bounded halting problem is an NP-complete problem. But this means that if P is not equal to NP, this isn't going to be a Turing machine feasible thing to do to analyze these bounded program behavior. This is assuming the Cobham-Edmonds thesis that the feasible computations are exactly the polynomial time ones. So the upshot of this would be that it's unclear what this move to considering only the kind of feasible computations or feasible inputs buys us, if in the end we're living in the NP-complete world anyway with trying to analyze this program behavior. Perhaps this means that analyzing negligence is going to require always some human or non-computable type input. So it's not the case that we can develop an algorithm that's going to feasibly tell us how programs behave for feasible inputs. So this is the kind of overall structure of the paper that I'm perhaps shooting for, is that whether or not people are responsible for a particular computational failure, whether we as a society are responsible for not working hard enough at developing our our debugging software, this is a matter that it is suggested, at least by results in computational hardness, both with respect to uncomputability and difficulty of computability, that this is something that is just not going to be universally solvable by some piece of software. There just is no program we could write that would enable us to solve these errors. And so in this respect, we are not failing as a species. We are not responsible for our software failure in virtue of a lack of effort. There just is no such program that we could develop to do the job. Okay, here's the second kind of argument or paper sketch that I'm thinking about a bit here. And this is the idea of looking at moral realism and trying to link this, or questions about moral realism, and trying to link this to questions concerning computational hardness. Okay, so what is moral realism? Moral realism is the view in metaethics that moral claims purport to report facts and are true or false if they get the facts right or wrong. So if we say, you should show compassion towards other people, let's say, this is a claim that is just absolutely true, and it's not relative, let's say, to society, for instance. So good examples here are things like saying slavery is wrong. That's another example. That is something that is objectively true. It's not the case for the moral realist that, say if we go back to Greek or Roman periods, that suddenly slavery was okay there because they inhabited a different cultural sphere or something along those lines. Now, the next piece that I need is the following view, and this is just going to add a kind of a priori addition onto moral realism. So, in addition to being objective, moral claims can be answered with an a priori warrant. So, this is just to say that I don't need to do any sort of empirical testing in order to determine whether or not a moral claim is right or not. I can just, by the dint of pure reason and thinking about it, determine, if I just thought hard enough, could determine whether or not a moral claim is right or wrong. There's then a question of, once we have this in play, of whether there is a recursively enumerable formal theory corresponding to these ethical concepts. Now, okay, this is suddenly we've leapt from fairly standard metaethical claims to something that's a very, very abstract idea of having some actually recursively enumerable formal theory for these ethical concepts. But I think it can be made a little more plausible when we want to say, look, perhaps eventually we could come up with some kind of theory of ethics. We could come up with a computer, and what we want to do is we want the computer to tell us how to behave. While this is a very abstract idea, it's not totally outlandish, and I think what I'm trying to do here, or would be trying to do if I wrote this paper, would be to examine what the kind of limits are in some given some kind of idealized sense of what we might be able to do. So I'm happy. This is, on the one hand, an assumption that is very, very far off. I don't think anybody thinks that we'll be coming up with, a universally acceptable, recursively enumerable formal theory for ethics tomorrow, but perhaps we want to say that this is at least, in the logical space of possibilities, given the current discussion. So what I'm going to argue is the following, is that our ethical position, and indeed whether we are failing as ethical agents, is contingent upon open conjectures in computational complexity, in particular whether or not P equals NP. Okay. Now, the key driver for some of these arguments is going to be the following principle, often attributed to Kant, and this is the what I'll call the ought implies can principle. So, very standard principle one often encounters in ethics, that if I or perhaps we ought to perform some particular action, then I or we must be able to perform said action. So you can't say that I ought to do something according to this principle if I'm unable to do it. Now, this is a very controversial principle. You might think it's relative to the particular domain of ethics you're considering. I just want to bracket these issues. I'm happy to take on board this principle for now and just say, look, if we have this as a general principle about ethics, how do considerations about computational difficulty figure into our thought about what it might be possible to do in terms of analyzing our ethical thought? Okay, so maybe you think that we ought to design an algorithm to tell us how to behave. This would be a possibility if we had, the relevant formal theory, you might think. Yeah, we have the theory, so let's design an algorithm that will tell us what the outputs of our ethical thought should be. Okay, so let's assume that there is a first-order recursively enumerable theory axiomatizing our ethical thought. Well, what do we know then? Well, by the Entscheidungsproblem, we know that the consequence relation for this theory is not going to be computable in general. So in particular, there's no way to tell in advance whether I ought to phi or not phi for some particular ethical action. Phi, right? So important here is that, so this is a general example of the kind of behavior we get with first order recursively enumerable theories. It's not like there's anything special about the ethical example, but it is special insofar as we have the ought implies can principle in play, right? So the idea that I ought to design an algorithm to tell me how to behave, right? That is something that is not actually in general possible, right? Because there's no way to tell in advance whether or not I should do a particular action. So although this is not, special to ethics, this general problem, it would be the same if I had a mathematical theory, right? There would be no way to tell in advance whether phi holds or not phi is a consequence or not phi is a consequence. It is important, given that we want to decide how to behave on the basis of this. So in the particular case of ethical theories, the Entscheidungsproblem becomes particularly acute. Good, so maybe we want to make a similar move as we made with the last argument I considered, and you say, look, this isn't that interesting, okay? We care about conclusions that we can come to feasibly. I mean, it's just sort of morally unfortunate if there are conclusions about my ethical thought that I could only come to in exponential time somehow. This is something I could never do, so in practice. So it's important that the algorithm we write for a computer is at least polynomial time. Again, let's just assume the Cobham-Edmonds thesis. Okay. But again, we have issues with P equals NP. So finding a consequence in polynomial time in general is in NP, right? So if P we have this contingency upon the status of P equals NP. If P equals NP, we could devise an algorithm to find answers to our really reasonably solvable problems in polynomial time. But if P does not equal NP, then it's entirely possible that this is not possible to do. Okay, so given the ought implies can principle, whether we should or ought to design such an algorithm is ultimately going to depend upon whether P is equal to NP or not, right? Such a design is on the table in the case where P equals NP, but it's entirely off the table if P is not equal to NP. So the kinds of things that are possible, and this is in general, this is not specific to ethics, is going to be very contingent upon the status of questions in computational complexity theory. But it's particularly acute in the context of ethical theories because we have this ought implies can principle in the background, possibly. Right? And in that case, whether or not you can legitimately claim that we ought to do something is going to depend exactly upon these computational constraints. Okay, so that was in the context in which we assumed we made this controversial assumption that there was this ethical theory, first order recursively enumerable, for axiomatizing our ethical thought. But what if there is no such theory? Okay, it's not the case that we can come up with some particular ethical theory, right? Well, there is a possible route to a similar conclusion if we assume mechanism, right? Recall that mechanism is the principle that the human mind is simulable by a Turing machine. Well, if mechanism is true, then there is some formal theory corresponding to thought, including our ethical thought, even if it doesn't directly axiomatize it. This is what Turing showed, that corresponding to Turing machines there are particular formal theories. Now, just to be clear about the distinction here, what we're saying here is not that this formal theory, axiomatizes our ethical thought directly, right? So, in the first case that I considered on previous slides, we're talking about, we introduce first order axioms for ethical thought and then we reason using them. Here, we're not saying that there are such first order axioms, axiomatizing the primitives of ethical thought. What we're saying is that, look, there is some chunk of a Turing machine or a run of different Turing machines that can be correlated with our ethical thought, or corresponds to the Turing machine simulation of our ethical thought. From that, you can then extract a formal theory, not for our ethical thought, just something that represents the Turing machine in question. Okay. So the issue we have then is, look, if we figured out this Turing machine, we might think we can figure out how to behave by simulating this machine, right? So we don't run a primitive formal theory axiomatizing ethics. We simulate the Turing machine and figure out, given the portion of it that corresponds to ethical outputs, what we should do. So the core issue we then encounter is that even if we had such a machine, we had a description of the Turing machine in inverted commas corresponding to human thought, even if we had such a description of a machine, whether or not particular consequences follow from that machine will be bounded by the Entscheidungsproblem, given the correspondence between Turing machines and formal theories, or it's going to be again relative to P equals MP if we restrict to feasible computations. Okay, so a different response might be, look, while we may be simulable by some Turing machine, we never discover the code for this machine. So you have this, it's very similar to what went on in the Lucas-Penrose argument. You have the claim that we are some Turing machine, we just don't know which one it is, and so we couldn't run it. Okay, so this is a different kind of response. So in either of these cases, what you have are computational constraints on what is possible given some meta-ethical assumptions. Okay, so in the case where I'm considering an ethical formal theory, the Entscheidungs problem in P equals MP might place some bounds on what we think it is possible to do. In the case where we have a description of the Turing machine in question, then we have computational constraints again imposed by the Entscheidungs problem and the P equals MP question. And in the case where we just don't have a particular description of the Turing machine, this is just a very significant consequence of considering these computational issues. If you think on this basis that we just can't get a description of this A, shows you firstly that we won't be able to simulate ethical thought by finding a particular Turing machine, and secondly that there's a kind of wider implication for trying to find computational models of the human mind, that you won't ever get one that is perfectly computable, because it will perhaps miss out the bit of it corresponding to ethical thought. So by considering these sort of quite esoteric cases of how ethical thought might be simulable or otherwise by a Turing machine, you get quite significant payoffs about what is or isn't possible. Okay, great. So I'm kind of interested by these two arguments. I'm sure there's lots of places where we can object to them. I think they're interesting, though, as they're both cases where kind of mathematical or computational results might be impinging on the space of ethical possibilities, or given other views, you might think there are actually kind of ethical ramifications coming from a theory of computation. This is just a kind of interesting interaction between different areas. Of course, there are, in both the arguments I gave, there are many places we can get off the boat. So, for instance, maybe you're just not a moral realist, and then the arguments don't apply. And I guess I just wanted to emphasize that my aim there is not to convince you that some particular conclusion or other is true about, what ethical thought is actually like, but just to articulate that by considering kind of mathematical or computational results, you might think that you can learn about ethical possibilities. So this is more an exercise in determining what the relationship between the mathematical and the ethical might be, as opposed to actually prescribing rules for ethical behavior, let's say. I take no stand on, for instance, the issue of moral realism. I'm not sure whether or not it's true. Okay, cool. Those are two arguments trying to link the theory of computation with ethical considerations. I don't know if they work. I'm sure there are objections, but I'd be really interested to get people's feedback on it. Thanks for listening.